Lab 5, Magnetic Braking with Faraday. The purpose of this lab is to understand the interaction between falling magnet and the aluminum foil tube. We're going to apply Faraday's law into this real-life model and compare observational and computational data. The procedure is to drop a bar magnet through the aluminum foil tube and measure how long it takes to measure the magnet to enter and leave the tube. And lastly, we're going to create a closed group model and compare results. The fundamental physics principles used are Faraday's law, Biot-Savart law, and induced currents, which is also equivalent to Ohm's law of EMF over R equal current. And lastly, Newton's second law, F equals ma, is going to be introduced in our lab portion. The observation from the measurements shows that the magnet falls through a tube in a slower speed than it would in free space. And some initial conditions are listed below, and based on the measurements from 5 trials, the average time that it took for the magnet to fall through the tube was 1.67 seconds. To look at the coding portion, I've substituted the initial values from previous slide into my code in order to initialize my coding, and I've copy-pasted the magnetic field equation from lab 3 in order to find the magnetic field of dipole. Then, by looking at d flux over dt, based on video 43, I was able to computize as shown. And gravitational force, as we know, is mass times gravitational acceleration, and current was based on Ohm's law, EMF over resistance. And to look at the force on loop, we use the equation current times circumference times magnitude of B field times sine theta. And lastly, to find the F net, we know it's the summation of all forces, and Newton's second law was used to find the updated velocity and position of the bar magnet. By looking at the results, we know the intensity indicates the magnitude of current in ring, and red ring represents clockwise motion of the current, and blue represents the counterclockwise current. The time in tube as shown is 1.528 seconds from the model, and as you can see, when the constant speed was reached in the velocity versus time graph, we know the F net was equal to 0. And some sources of errors that could account for the difference in observation and model value is based on human error and also using a off dipole moment from lab 3. The reason why we know from computational model that the red represents clockwise current and the blue represents counterclockwise current is based on the Faraday's law. As you can see on the right, as I have illustrated, the blue ring shows the counterclockwise motion of the current because the dB/dt in this case is pointing down, but the negative dB/dt will be pointing up, and therefore based on right-hand rule we can apply that current is going to rotate in counterclockwise motion. And this applies to the bottom red ring as well, and therefore based on right-hand rule the bottom ring will have a clockwise current motion. And if you flip the magnet around, the rings are also going to be flipped bottom up because now the top is going to have a clockwise current and the bottom ring will have a counterclockwise current. What if the resistivity of the conductor were reduced as close as possible to 0? We know the induced current will increase due to Ohm's law, and thus the magnetic force will increase, and therefore magnet will take longer time to fall. And if there were holes or any slots cut into the tube, we know resistance will increase due to less complete rings. Induced current then decreases, thus the magnetic force will decrease as well, and therefore magnet will take shorter time to fall. To conclude, the time taken for magnet to fall through the aluminum foil tube was 1.67 seconds in real life and 1.528 seconds in computational model. And to make a more accurate measurement, we should redo lab 3 to find the magnetic dipole moment and use a software like Tracker to find the time in tube.